Hey guys, today we're going to be climbing the cosmic distance ladder. No, it's not a literal ladder, though that'd be pretty awesome. The cosmic distance ladder is how astronomers measure distances across the universe using a series of overlapping techniques. It's a brilliant system, and without it, we'd be pretty lost at space. So let's break it down. So what is the cosmic distance ladder? It is a series of methods astronomers use to measure distances in space, starting with nearby stars and working all the way up to the edge of the observable universe. What does this have to do with distance? It takes distances to stars and tries to explicate it to distances in the observable universe. The first rung gets you started, but to reach higher distances, you need new tools and new techniques. Each rung depends on the ones below being accurate, so getting the foundation right is critical. Let's start with parallax, the first rung of the ladder. Parallax measures how a nearby star appears to shift against the background as Earth moves around the Sun. Here we have a diagram of Earth going around the Sun, and there's a distant star that we want to look at. When we look at this distant star from one side of our orbit versus the other side of our orbit, it appears to move with a slight shift. This shift, this angle, is called the parallax. We see this effect happen to us as well. Hold your thumb up or a pen up in front of your eyes at an arm's length distance. If you do this and close one eye, the pen or your thumb will seem to be in the same position that it was before. However, if you close the other eye, this pen seems to shift positions. Using this difference between the original pen position and the shifted pen position, we can essentially find out how far the pen is from our eyes. The same principle applies to Earth's orbit. When we take a picture of a star from one side of Earth's orbit and the same picture of the same star from a different side of Earth's orbit, even though the star is very far away, it still seems to have shifted just a slight bit. And using that parallax angle and simple trigonometry that we've learned in high school, we can find out how far this star is. Parallax is pretty useful for stars within a few hundred light years. But beyond that, the angles get a bit too small to measure accurately. So it's time to climb to the next rung. Cepheid variable stars, our second rung. These are stars that brighten and dim in a regular cycle, like a cosmic heartbeat. They have pulsating brightness, and here's the key: the period of their pulsation. So how long it takes for them to go to the minimum brightness, to the brightest they can be, back to dim, and the brightest, etc., tells us their intrinsic brightness, their absolute magnitude. We can easily plot a period of pulsation versus absolute magnitude diagram and see that there is a very obvious relation between the period and the luminosity. And with the known luminosity, we can get the distance specifically to the Cepheid variable star. How? It's all thanks to a relationship discovered by Henrietta Swan Leavitt in the early 1900s. By comparing how bright a Cepheid appears to its true brightness, we can calculate its distance. Cepheids are like lighthouses for nearby galaxies, helping us measure distances up to tens of millions of light years. Cepheid variables are one kind of stars and objects in space that we call standard candles. We'll talk a little bit more about what standard candles are later in this video, so stay tuned. When we need to measure even farther distances, we turn to type 1a supernova. These are explosions that happen when a white dwarf reaches the Chandrasekhar limit, about 1.4 times the mass of the Sun. This intrinsic limit of type 1a supernova causes all type 1a supernova to explode with the same intrinsic brightness. By comparing how bright they appear to their true brightness, again, we can measure distances to galaxies billions of light years away. And yes, we're literally using exploding stars as yardsticks. Here we can see an example light curve of a type 1a supernova. Over time, no matter how the shape of the curve looks, they all still end up having the same peak magnitude. Not on our plots, but the same absolute magnitude. Again, type 1a supernova is one example of what we like to call standard candles, which includes Cepheid variables, RR Lyrae stars, and the tip of the red giant branch.
Cepheid variable stars and other similar objects are what we call standard candles. When we see an object in space, we can see its brightness. But we know that brightness of an object depends on how far it is. This flashlight may seem dim to you, but if I bring it really close, it'll get brighter. However, we need to find a way to standardize this brightness. We standardize this brightness with what we call absolute magnitude. Absolute magnitude is the brightness of a star if it is a certain distance away, in this case, 10 parsecs. For example, our sun is a very bright star in the sky, but there are other brighter stars out there. However, they don't seem as bright to us because they're really far away. So that's why the brightest star in our sky is the sun. But if we put the sun and all these other stars at an equal distance away from us, 10 parsecs, we'll see that the sun isn't one of the brightest stars, not even close actually. There are much brighter stars out there. How does this relate to standard candles, you might ask? With standard candles, we know how bright the object is. And if we know how bright the object is, we can find out how far it is. Take this flashlight, for example. We see that this flashlight is a certain distance away from us. However, like I said, if we get closer, the light that we receive from this flashlight is much more. This light falls off following the inverse square law. The farther we are, the intensity goes down by 1 over distance squared. In a similar fashion, even though that's not the exact same law we use for standard candles in space, we can find out how far the object is by knowing how bright it is. We could only know how far the flashlight was from us because we knew how bright it is.
Thus, using the standard candle, where we pretend a candle is just the same as a galaxy, in a sense, once we have the luminosity of the candle, or of a galaxy, we can use its observed brightness to calculate the distance to that standard candle. This distance we can measure using various equations, such as this one. Type 1a supernova are what we call standardizable candles. They're not perfect standard candles, but by using the color and stretch of their light curves, we can essentially standardize them and find out their exact absolute magnitude. And like I said, using this absolute magnitude, we can find out how far the Type 1a supernova is. So there we have it. We've completed the cosmic distance ladder, more or less. I mean, there's actually one more part of it. So let's find out what that is. The top of the cosmic distance ladder is what we call Hubble's law. This law was determined by Edwin Hubble when he plotted galaxy distances against the velocity that the galaxies were receding or going away from us. The distance ladder was very important as it helped us find the distances to these galaxies. The slope of this plot is what we like to call today Hubble's constant, or h0. And this h0 value tells us how fast the universe is expanding away from us. Using standard candles, we end up getting an h0 value of about 73.8 kilometers per second per megaparsec. So what that means is that the farther away a galaxy is, the faster it is moving away from us. By about 73.8 kilometers per second, every megaparsec farther you go from us. Galaxy velocity we find by using some sort of Doppler shift, essentially. For those of you who know, get galaxy velocity by using redshifts. However, some scientists get that the Hubble constant is about 67 kilometers per second per megaparsec using a different technique, which should also work. The uncertainties for these values do not overlap. So how can we get different values for h0? I mean, that makes no sense, right? We'll talk about it in the next video. So that's the cosmic distance ladder, from parallax to Cepheids to supernova and beyond. It's how we measure distances across the universe. Each rung builds on the last, and together, they give us a way to explore the cosmos and even figure out how fast the universe is expanding using Hubble's law. It's pretty mind-blowing, right? And we made it to the top. What do you think? Which rung of the ladder do you find the coolest? And which method do you think was the most innovative? Let me know in the comments. Don't forget to like, subscribe, and keep looking up, guys. See you next time. Don't forget to like and subscribe. It's free, and you can change your mind at any point in time, and it really helps me out as well.